Good evening. I'm Spot On Weather meteorologist Matthew Euler, and I'm proud to present the 2017-18 winter forecast for Southeast Virginia. So let's go ahead and get right going into the discussion. All right, so for winter forecast considerations, what we have taken into account to produce this year's winter forecast are a few things I must mention. First, we'll start off with the emergence of La Nina conditions and weather conditions associated with the past La Nina year winters for the Mid-Atlantic region in general. Second, we'll take a look at the active hurricane season across the North Atlantic Ocean basin. We will take a look at the factor of extremely high ACE values, or accumulated cyclone energy index values, and the potential energy deficit basically across the Northwest Atlantic Ocean basin. In parentheses here, I've got less nor'easter frequency, and I'll explain that more as we get into it. Thirdly, we need to talk about the October Siberian snow cover, and Dr. Judah Cohen, he's referenced in the video, from AER. He has an extensive research that has been done talking about October Siberian snow cover and its impacts on the mid-latitude winters. Fourth, we need to talk about the wild card teleconnection patterns that we hear so much about during the winter season. The North Atlantic Oscillation, the Arctic Oscillation, the Pacific North American or PNA pattern, and the Madden-Julian Oscillation. And then lastly, we will talk about sea surface temperature anomalies and the location, where those anomalies are located, and how that affects the long wave ridge versus long wave trough placement, how that impacts the jet stream configuration. As an example, back 3 winters to 4 winters ago, we had a warm blob in the Gulf of Alaska where we had abnormally above normal sea surface temperatures into the Gulf of Alaska, which produced a upper level ridge or high pressure system, which basically locked itself in place across the western U.S. and resulted in extreme drought conditions across California, as an example, and other locations across the West. And then, as there was an upper level trough over the West, there was an upper level ridge across the West. There became an upper level trough in the eastern U.S. So we're going to take a look at the sea surface temperature anomalies. All right, so let's first start our talk about the emergence of La Nina. I will start by saying that this may be a 2-part video. There's just so many factors, and I really don't want to rush through the discussion on these factors and how we came up with the winter forecast. So part 1, this is part 1, and I may be doing a part 2 to finish off the winter forecast video. All right, so let's start off with the emergence of La Nina. All right, so first of all, I must stress or emphasize that La Nina and its impact on our winter weather here in Southeast Virginia is really dependent on the strength of the La Nina. If it's a weak La Nina, we can expect on average slightly below normal temperatures and slightly above average snowfall. I will remind you that the average snowfall for Southeast Virginia in the wintertime is about 7 inches. On the other hand, if we have a strong La Nina, we typically have warmer than normal temperatures with below normal winter precipitation or below normal snowfall. So these are some years that we picked out in the past in which there was a weak La Nina, starting with 1954 to 55, and then as recent as 2016-2017 winter. And then we would take a look at strong La Ninas, 73, 74, 75, 76, 88, 89, 1998, 99, 1999 and 2000, 2007, 2008, and 2010, 2011. So these are the years we're looking back at the La Nina patterns and what typically has happened. I'm going to emphasize this in a moment. I do want to define what a weak La Nina is. Basically, that is when our sea surface temperatures across the equatorial East Pacific, so generally in this area down here, okay, that's when the water temperatures are 0.5 to 0.9 degrees below normal. And with a strong La Nina, the sea surface or water temperatures are actually 1.5 to 1.9 degrees below normal, generally in this region, which we call the Nino 3.4 region, which is bounded by these latitude positions and longitude positions. 5 degrees north to 5 degrees south latitude, 120 degrees west to 170 degrees west longitude. The source, by the way, of these definitions was from Jan Null. She is a certified consulting meteorologist. So overall, the weather pattern when you have a La Nina, okay, you have a variable jet stream represented by this brown line here. And by the way, the image is courtesy of NOAA, as we have depicted on here. You have a variable Pacific jet stream that basically moves across the Pacific into the Pacific Northwest. And as this high-speed ribbon of air or jet stream crashes into the north-south oriented Cascade Mountain Range, it results in a much above normal precipitation over the Pacific Northwest. And also, you'll see a colder than normal pattern setting up from eastern Alaska down through western Canada into the upper Midwest and the northern Plains states. The purple line here indicates the polar front jet stream axis, this purple line. And what it shows is a huge ridge over the top of this southern branch of the jet stream. So you have this high pressure or blocking high sitting in the Gulf of Alaska. You have more of a northwest flow directed, clockwise flow around the upper high, and more of a northwest flow bringing colder air down again into eastern Alaska and western Canada into the northern plains. And notice what happens down here in the south during a typical La Nina winter. You have drier than normal conditions, and then there is a wetter pocket or above normal area right here in the base of this trough, this long wave trough, generally situated from Ohio, Indiana, down to Tennessee and western parts of Kentucky. And if you notice for our area, the red area here indicates warmer than normal temperatures. And this is a typical pattern for a La Nina winter. And again, I must define La Nina as a cooling of the sea surface temperatures across the equatorial East Pacific Ocean. And that's exactly what a La Nina is, below normal sea surface temperatures across the equatorial East Pacific. All right, so let's take a look at sea surface temperature anomalies right now that indicate La Nina is occurring. All right, these blue areas represent areas where the sea surface temperatures are below normal. The red and orange areas indicate areas where the sea surface temperatures are above normal. So as you can see, right in this area, you have colder than normal temperatures. This is the equator, this line right here going across. So the equatorial East Pacific off the coast of South America is showing signs of La Nina. And in fact, there has been a La Nina watch issued by the Climate Prediction Center, which is a branch of NOAA. Here is the model La Nina forecast. And so basically, these are all the dynamical models. All these are dynamical models, and there are statistical models thrown in here as well. And at the bottom here, we have the months are abbreviated. For example, OND is October, November, December. NDJ is November, December, January, and so on. Okay? And this 0 degree line is generally where that's where there's no sea surface temperature anomalies. Notice how the temperature dips down below this 0 degrees Celsius line. So that indicates that we're expecting colder than normal sea surface temperatures across the equatorial Pacific. And you'll notice how it gets a little bit stronger, the La Nina, as we progress into the wintertime. Here's November, December, January. Here's December, January, February. And here's January, February, March. All right, so now let's take a look at snow and La Nina winters. All right, so these are the top 15 snowfall amounts or events recorded in Norfolk. All right, so I circled the main areas that are actually considered strong La Nina winters. Okay, so we had in February of '89, we had a 15.4-inch snowstorm. January 8th to 9th, 1973, and then February 23rd to 24th, right down here, there was 9 inches of snow. And again, that's associated with, this is a table of weak, moderate, and strong La Ninas. These 3 of the top 15 snowstorms of all time in Norfolk actually occurred during a strong La Nina. Okay? So just because something is typical for a winter based on La Nina strength does not necessarily mean it's going to happen. And here again is a breakdown of the weak La Nina winters, the moderate La Nina winters, and then the strong. I'm pointing out 3 of the top 15 snowstorms again for Norfolk occurred in strong La Nina winters. Something to keep an eye on. Additionally, now we move on to factor number 2 in developing our winter forecast. We're going to talk about the active hurricane season that has been this year across the Atlantic Ocean basin. First of all, I just want to tell you that energy generally transfers from lower latitudes, the equatorial regions, hotter equator, to higher latitudes or the colder polar areas. And this is a normal thing. Why? Because the atmosphere is always trying to establish itself into equilibrium, into a certain form or semblance of balance. And storms are mechanisms for reestablishing the critical balance in the atmosphere. So this, during the above normal hurricane seasons, what happens is more potential energy is used in reestablishing this critical global heat balance, or the equilibrium I was mentioning here. So during above normal hurricane seasons, during the warm time of year, such as 2017, we have a lot more potential energy that has been used up. So if we have greater potential energy being utilized by hurricanes during the hurricane season this year, there is increased likelihood of less or a lower number of winter storms or nor'easters during the cold season along the United States East Coast. And why is that? Because the hurricanes have used up most of the potential energy already to redistribute heat from the lower to higher latitudes. So there's less available potential energy for the nor'easters or those East Coast winter storms. All right. And just to prove how active the hurricane season's been and how much energy has been utilized in the hurricanes this season, we refer to what's known as the Accumulated Cyclone Energy Index, or ACE. And the ACE takes into account both the storm's intensity and the duration. Current value across the North Atlantic Ocean basin is 219.5, compared to the climatological norm of 90.1. So as you can see, 219.5 is where we're currently at for ACE. 90.1 is normal. So as you can see, there's an amazing use of available potential energy by hurricanes. All right, I'm going to end this as part 1, and I'll be right back with part 2.